Okay, so so far we've talked about the integral, specifically the indefinite integral, as being the set of all antiderivatives of our function. Antiderivative being kind of the opposite of a derivative, right? So it's going the other way. So instead of this being the derivative of this, we've switched it, and the derivative of this function is our original function. So this is a little f, and that's big F. So we're going to connect this idea in a later video to this idea of the definite integral. And so the definite integral looks real similar. Same symbols, we have our dx again, but we have numbers here. And so this is from a to b. So this is the integral, the definite integral from a to b of f of x dx. And how we interpret this is the area under the curve between x equals a and x equals b. And so we're looking at kind of the area here. This here would be the definite integral from 1 to 3 of my function x squared dx. So this is kind of a tricky area to figure out because we got this curved side here. We do have a formula for that curved side, but we don't have a good formula for an area of, a quadrilateral with a curved side. Quadrilateral being a four-sided figure, right? So an easier quadrilateral to calculate the area of would be a rectangle. So what we're going to do is we're going to approximate this area using rectangles. Now we could use one rectangle, and that would be a pretty bad approximation, right? Because we'd have either a bunch of area that's not under our curve, or if we did like this rectangle, we'd have a bunch of area that's also not in our curve, or that's not being accounted for. So the more rectangles we do, the better. So what we're going to do is we're going to approximate this area. We're going to approximate this area by looking at the, let's do 4 rectangles. So we've got like this. Now we want our rectangles to, it's not perfect, oh well. We want our rectangles to have kind of a regular width, a nice predictable width. And we'll call that width delta x. Now, how do we figure out delta x? Well, if we want it to be the same, for each one, we're going to look at the length of our interval. So our interval being where we start to where we end. So the length of our interval here is 3 minus 1, or 2, divided by the number of rectangles we're going to do, and we're going to do 4. So here, 3 minus 1 is 2, divided by 4, this simplifies to 1/2, which we can also just kind of see here on this picture. Now, we haven't talked about how high these rectangles are. They're not rectangles yet, right? We still have this curvy part. So we could do this a few different ways. We could look at, for each one of these rectangles, we could look at the left side of that rectangle and or left side of my interval, of each sub-interval. And we could say, okay, well, that's going to be the height of that rectangle. We could look at the midpoint between my sub-interval, and we could say, okay, well, that's going to be the height of my rectangle. Or we could go to the right side, and we could say, okay, that's going to be my rectangle. For the work we do in class, we're going to use the right-hand rule. It ends up being a little bit easier with the math later. So we're going to use the right-hand rule, meaning we're going to have the right-hand side be our rectangles. So for each one of these, we're going to do the right-hand side, and then my graph's not exact. I eyeballed it. So it should be up here, but to try to keep it where it should be. That one's going to be about there, and this one's going to be about there. So we've got the right-hand side of each of our sub-intervals dictating, how high our rectangle is going to be. And then we just add up the areas of the rectangles. And so it's, length times width. So, this side of the rectangle is going to be, f of x, whatever the x is. And here we've got, 1.5 to 2.5. knowing me, I'm gonna have that height be fractions, right? So this one, it's f of 1.5 or 3/2, and then times the width times our delta x, which is 1/2. And so this here, this height times this width, this is the area of our first rectangle. And then we're going to add to that the area of our next rectangle. So that's going to be f of 2 times 1/2. So that's area 2 plus f of 2.5 or 5/2 times 1/2. That's our third area, plus f of 3 times 1/2, and that's our fourth area. And then to just crunch the numbers here. So this was approximate because this is not exactly the area we're looking for. But this is equal because this is going to be equal to what we had up there. So this is 3/2 squared times 1/2 plus 2 squared times 1/2 plus 5/2 squared times 1/2 plus 3 squared times 1/2. Let's just simplify here. 9/4 times 1/2 plus 4 times 1/2 plus 25/4 times 1/2 plus 9 times 1/2. And then let's see, we need common denominators here. We're going to multiply, so we get 9/8. 4/2, let's see, would be 16/8. So plus 16/8. 25/8. 25/8 plus, do that right? This would be 16/4. Yeah. And then let's see, 9/2 would be 36/8. 36/8. And so let's see, 9 plus 16 is 25. Plus 25 would be 50. And then altogether we get 50 plus 36 would be 86/8. Which is, our approximate area. So we're saying that, this area here is approximately 86/8. What number is that? 86/8 is, approximately 10.75. So that's approximately our area here. Now, in later videos, we're gonna figure out what's a better way to figure out what that area is. There is a way to get it exact, and so that's kind of our task here with figuring out what the definite integral is how do we figure out exactly what it is? So we'll get to that in a later video. That's the basic idea of what this definite integral is, and what this process is of making these rectangles. This is called a Riemann sum.